So, hello everyone. Today we have the pleasure to listen to a webinar that will be given by Dr. Guillaume Miquelard from the PMMA laboratory in Paris. So I just say a few words about Guillaume, who defended his thesis in 2007 at the ESPCI at the SIM laboratory. He was with Dr. Constantino Creton and Dominique Ourdet. And then Guillaume did a postdoc at UMass Amherst at the Department of Polymer Science and Engineering in the group of Al Crosby. And then he came back for another postdoc at the Laboratory of Physics Statistics in Orsay. So Guillaume will present us his research on polymer films made by multilayer coextrusion. So please, Guillaume, whenever you're ready.
Thank you, Olivier. So everyone sees my presentation, okay? Olivier, c'est bon pour la présentation?
For me, that's fine. I think everybody.
Okay, thank you. So thank you, Etienne, for organizing this. It's a really great idea, and I'm really happy to see people are following these seminars. It's kind of weird to talk out loud in front of his computer without seeing anyone, but I guess we have to get used to this. So I'm a maître de conférence in Le CNAM in Paris. So that's the building you see here. Some of these parts are from the amongst the oldest in Paris. This here, the chapel, is from the 11th century, and this tower here also. But my lab is in another place in Paris. It's in the École des Arts et Métiers. And it's a lab about which works on processing, engineering, and mechanics of materials. So today I'm going to talk about processing of polymers, and especially coextrusion. And I'm going to couple that with structural properties relationships of polymer materials and a bit of physics of instabilities to talk about the limitations of this process. So there will be some applied stuff and some more fundamental one. So just to start with a basic idea of materials engineering is how to make advanced materials, architectural materials with a controlled structure that can bring some specific properties. So it's a really general idea, and there are two ways to think about it. And probably looking at the previous seminars, most of the chemists are more thinking about bottom-up strategies, which means that you synthesize new polymers with functionalities that are new or special. Then you try to stack these molecules to make materials with new properties. So this is really fancy. You have to make new molecules, but you have to then go to the upscale to make materials. So to make materials, what is more simple is a top-down approach, where you use processing tools and you try to modify them or to adjust them to achieve the best control you can on the nanostructure. So of course, when you use processing tools, you are using polymers that are less well defined than with the bottom-up approach, but you have higher quantities, and the processing tool is more harder to control. So usually you don't achieve the same scale. But if you really think about bulk materials, usually top-down has some advantages over a bottom-up approach. So just one quick slide about the bottom-up approach. Just one example that probably all of you know. It's the block copolymers. So you define polymers with two different structures that you bind with covalent bond. And you have these phase diagrams that are based on the Flory interaction parameter, which I will come back later on, the degree of polymerization of the two polymers, and the volume fraction. And this phase diagram will define how the copolymer will phase separate. But because you have these covalent bonds between the two polymers, this is a nano-phase separation, and you can do these really nice structures such as lamellas that are presented in the picture here. So these copolymers are mostly used for surface application. So you can use that to do some lithography beyond conventional optical lithography, because you have definitions at the nanometer scale. It can be used in bulk applications, and I will mention one later on, but usually this, the limitation of that is that you cannot have this organization up to 1 millimeter thickness or more. So now I'm going to focus on the top-down approach and thermoplastics processing, especially extrusion. So I'm not sure all of you are familiar with extrusion, so I'm just going to, hopefully it works, show 1 minute of a YouTube video that shows how it works for those who don't know. So let me try that. So the video lasts 1 minute, and usually when I do a real seminar, I speak instead of the speaker, but I think here it's easier if I let the speaker go on.
Guillaume, can you put the loud a bit? Can you
louder?
Yes, louder, please. Or maybe you can comment.
Okay, so you see it's quite big machines, and you have to use a really large amount of materials, so quantities on the order of 10 of kilograms, so not as well defined as most chemists are using. And the idea is that you have to bring heat to break the weak bonds between the macromolecules, and even more heat so the molecules can slide despite the entanglements. So this heat is not enough because it will take a really long time to slide. So what you have to do is also to shear the material, as you saw in the video. So now I'm going to talk about coextrusion. So extrusion is what I presented before, but coextrusion is the same thing, but with two different polymers and two extruders that you connect together. So in one extruder, you will put one polymer, in the other one, you will put another one. And at the end of the two extruders, you will have a die that will connect the flows of the two polymers. And out of the die, it will cool down and become a solid again. And you have a co-extruded film with two layer of the film on top of each other. Depending on the shape of the die, you can have 2 layers, one on top of the other, or 3 layers, one polymer in between 2 layers of the other one. So that just depends on how you structure your feed block and your die. This strategy of co-extrusion is really well known and has been used in the packaging industry for decades. And actually what you do in the packaging industry is you use one flexible polymer, so usually polyethylene, and one glassy and really barrier against gas polymer, which is usually EVOH. So the idea is that the polyethylene is really cheap, really easy to process, and really flexible, so to wrap your food so it cannot be wasted, it's good. And the EVOH is really crystalline, and it will have good barrier properties, so it will prevent oxygen to go through and make your food or your meat rot. But this polymer is really expensive, and also it's quite hard to process. So the idea is to make a sandwich of the two with a large amount of polyethylene and a small amount of EVOH, just to get the good balance between flexibility, ease of process, price, and barrier properties. So that's the basic idea, and it works really well, but there is one problem, is that PE and EVOH, they don't like each other, so they don't stick to one another. So if you make a film of these two polymers, the 2 layers will simply peel off really easily, they will detach, and so your film will not have good mechanical properties. So what you have to do is add a 3rd layer, an adhesive layer, which is usually a polyethylene with some maleic anhydride grafted molecules on it. And it will bind, it will make the polyethylene and the EVOH bind together. So actually you are not using 2 extruders, but 3 extruders to make a 5 layers film. So I'm going now to explain a bit more fundamentally what is the role of this tie layer. So it's this equation on the right is the thermodynamics of mixing. So for 2 polymers, you have this type of equation with an entropic term and an enthalpic one. And this one depends on the flow interaction parameter. And for polymers, it's usually non-favorable to the mixing, while the entropic term is always favorable to the mixing. But because you have here N1 and N2, which are the degree of polymerization, which are big numbers for polymers, the entropic term, which favors mixing, is really small. And because the flow interaction parameter is usually quite high for polymers, then usually the energetic term wins, and the polymers are immiscible, so they don't like each other, you cannot mix them. Another notion that is important in processing is the compatibility. So compatibility and miscibility are a bit different. 2 immiscible polymers can be, in some cases, compatible, which means that they will, despite the fact that they immiscible, they will still have some interactions between one another. But in the case of PE-EVOH I showed before, they are immiscible and they are also incompatible, which means that they won't bind at all together, and that's why you have to add this tie layer. So the molecular reason for that is the interface between the 2 polymers. So the interface is the region between the 2 polymers, or between the 2 interfaces in which the polymer blend. And this region is really small in thickness. For immiscible polymer, if you put some numbers in this, so B is the length of the monomer, and chi is again the flow interaction parameter. For incompatible polymers, this number is only a few nanometers. So only a few monomeric units are actually binding the interface. So that's why it will detach really easily. It's below the entanglements in this region, so it will detach really easily, and the films won't have any mechanical properties. But if you add a compatibilizer, which is usually a copolymer, it will segregate at this interface. So it will expand the size of the interface. And maybe you can have 50 or so nanometer as an interface, which is above the entanglement size, which means that you will have some interfacial adhesion between the two faces, the two interfaces, which means that your film can have good properties. So what is this compatibility doing in the mechanical properties? So let's start, for example, what is on the right. So on the right, you have two polymers, polypropylene and polyvinyl chloride. When you mix them together, you have this blend here, which has really bad properties. So you lose all the elongation at break. And for the modulus, you have simply something that is in between the two initial moduli. So because there is no interface or really small interface, no compatibility whatsoever, the properties of the blend are totally poor and the blend is useless. Now, if you have some better thinking and you add some compatibilization and say you blend some PMMA, which is a brittle polymer, you blend in PMMA some rubber particles, then your PMMA will be toughened. It will have a larger elongation of break, but it is only the case if you can add some, if you increase the interface. And to do that, you have to decorate, for example, the rubber particle with some PMMA. So then when you put this PMMA, this rubber particle in the PMMA, because of the grafted PMMA at the surface, it will blend well with the PMMA, and you can have a material that have then good elongation and good impact resistance. So you see that to blend polymers, there are some strategies, and you have to think a bit better than just, okay, these two polymers interest me, I just have to blend them, and it will work fine. So now I'm moving back. I told you some generalities about blend, and I'm going back to coextrusion. So to make coextrusion work, you have to think about the rheology a little bit, because in the barrel with the screw, you have some shear to the material, and it's in the melt. So you have to think about the rheological properties of your polymer. And because in the die the two polymers connect, the rheological properties of the two polymers have to be connected. And actually, for it to work, you have to make the rheological properties quite similar for the two polymers at the extrusion temperature and in the shear rates that are typical for coextrusion. So if you work with matching rheological properties, then you can make nice multi-layer films. But if you don't, then you will create some instabilities that can break the structure of your films. So here on the left, you have a multi-layer film with 10 layers or so. And because the ratio of the two viscosities are matched, you have relatively homogeneous layers. If you have one order of magnitude of difference between the two viscosities, then the structure will break. It is also the case if you have, for example, one polymer that has a really larger elasticity than the other one, then your structure will be really deformed by this difference in elasticities. So people have known for a long time that to have coextrusion work, you have to have similar viscosities and similar elasticities at the extrusion temperature and at the shear rates that are typical in coextrusion, which means in this gray region, about 10 radians per second. So now I explain you how to make 3 or 5 or maybe 9 layers, and I want to switch to real multi-layers, so say 1,000 layers. How can I do that? So you saw previously that with 2 extruders I can make 3 layers, with 3 extruders I can make 5 layers. So if I add more extruders, I can make maybe 10, 20, or 30 layers. But of course, at some point, I can't add more extruder in the system. So I will be maybe limited to 30 layers. So if I have 30 layers, I have something that looks like that. And my film, which looks like that. So in the thickness, you have 30 layers. The thickness total is about 100 micron or so. So each layer is a few microns. But now, what can I do if I want to have nano layers? And that's going to be the focus of my talk now. So maybe your first question is, why do I want to make nano layers? Okay, the word nano is fine, but maybe there is some interest beyond that. So I can make some reference to nature. It's something that is really classical. I usually don't want to make it too often, but in some cases it's worth it. So nacre, for example, is a nanostructured material which has really good mechanical properties because it's both tough and deformable. And this is because you have this layer that looks like brick and mortar. So you have some bricks that are really tough and some mortar that is some kind of protein or polymer, I don't really know, that can bring some elongation at break. And also that will delay the fracture because to fracture the material has to build a path between all these nanostructures. And in the case of polymers, going to nano is even more interesting because it has been known for quite a while that polymers can display really new or interesting properties when they are confined at scales that are similar to their radius of gyration, say, so 20 or 50 nanometers. So people have seen that the glass transition temperature can be drastically modified. The mechanical properties can also be modified. So there can be some interest to try to go down to this nanoscale. So now I want to make these multi-layer films with 1,000 layers that each has nanometric thickness. So what will I do? I will do simply this. So it's actually quite simple. I put my two initial extruders with a feed block. So I have my 3 layers film and I'm still in the melt state. So instead of going out to cool it down and have my final film, I put this polymer flow in a channel, still under high temperature, so it won't cool down. And I use multiplying elements, which are these little elements. So it's little pieces of steel that look like that. It's a couple centimeters long, couple centimeters high. And what they will do is they will cut the flow in two. So you see here you have this axe that will play a role like a knife. So it will cut the flow in two. And then you have this little step. One goes up, and on the other side you don't see it, but one goes down. So one part of the flow will go up, and one part of the flow will go down. Then the flow will spread, and then they will merge again. But because it's all in a channel that has a constant thickness, the total thickness of the flow is the same, but you add 3 layers at the start, you have 5 layers after the mixing elements. So each layer has a thickness that is divided by 2. So here you have 3 layers, you cut and you recombine, you have 5 layers, the thickness total is the total thickness is the same. So basically, each layer has a thickness that is divided by 2. And if you do that one more time, you have 9 layers, and one more time, and one more time. So it's called the baker's transform, and it's how, for example, in Chinese restaurants, you see sometimes they make noodles, or it's how the baker make the pâte feuilletée in France also. So if I do that with 10 multiplying elements, at the end, my film will have, say, 2,000 layers. And because its total thickness is 100 micron, each layer will be something about 100 nanometer or less. If you look at that on the AFM, so I look at it in the thickness direction, and you have all these layers, all this millefeuille structure. And you can see that in black or in brown, the layers are maybe 100 nanometer, and the yellow ones are another polymer. and are a bit thicker, so maybe 500 nanometers. So that's how we make nanolayers, or films with nanolayers inside the films. So what I have to mention now is that it's actually quite old, this innovation or this process. It has been patented close to 50 years ago by Dow in the United States. And you can see that the first patent in 1966, the design is quite similar to the design I showed you in the previous slide. And I don't think it had many applications in the industry. The only one I know is iridescent films. So I don't know much about iridescent properties, but it's when you look at the film from another angle, it will change its color. So that's what is used to, for example, protect your screen, computer screen, from being seen by someone else. So I don't know if this film, you can see it, but me, I can see that it has some iridescent properties. So one application maybe more fancy than iridescent films has been developed in a lab. So it came from the industry, but then it has been taken by a lab at Case Western Reserve University in the United States by Professor Baer. And he worked a great deal to develop barrier materials, as I mentioned earlier, or hyperbarrier materials. And what he showed is that for some polymers, not all of them, but if you choose the polymer well, you can buy. So this is the barrier property or the permeability of the PEO polymer. So the lower it gets, the better it is for the barrier, as a function of the layer thickness of the film, of the PEO layers, sorry. So if I go from micron scale to nanoscale, the bulk permeability of PEO is there, and the PEO, the confined PEO permeability is there. So I can lower my permeability by almost 2 orders of magnitude by going from micron thick layers to 50 nanometer thick layers. This result has been also observed for other polymers. So now the question is why this reducing the thickness will enhance the barrier properties. So you probably all know that when you don't confine your polymer and you let it crystallize isotopically, it will usually do these kind of nice structures that we call spherulites that are micron size, even 10 to 100 microns, and that are actually made of lamellas that are really thin, about 10 nanometer in thickness, and really long. And you have this assembly of lamella that form a spheric shape. Now, if I confine my spherulite, what will happen is that I will go from this relatively isotopic shape to something oriented in the direction of the thickness, so of the walls of my confiners. So if I go from microns to nanometer, then instead of having lamellas in every direction, I will have one lamella that is oriented perfectly in the direction of the wall. And because this lamella is really well oriented, the gas molecule has to follow a bigger path to find a hole in this lamella. So here it's isotopic, so the gas molecule can find its way through the exit in the amorphous phase quite easily, while here it's really like a wall, so it has to go all this direction till it finds a really weak spot, then it can go this way. And so it will increase the path and really increase the permeability, the impermeability of the system. And you can see that that's actually what happens. So again, it's AFM measurements. You have these random lamellas, and here you have these really well-oriented lamellas that are really confined and the size of the layer is about here 50 nanometers. So the permeability again looks like that. So reducing the layer thickness will increase will create some interfacial and confinement effects, and this can in turn bring really new properties to the system. So another application, maybe I will try to make this one quicker with this system, is mechanical properties. So, and this was made in our lab. So we tried to design laminated organic glass, so glass that can resist really impact. And to do that, usually what you do is you have one organic layer, one inorganic layer, one organic layer, one inorganic layer. And here we made some all organic glass. So it's the same idea as what I presented before with the rubber particle inside the PMMA. But instead of having a rubber particle, we tried to make layers of rubbery materials. So to do that, we used not really direct rubber material, but tri-block copolymer to improve the affinity, again, in the same manner as here, to improve the affinity between the rubbery block and our matrix, which is PMMA. And with this multi-layer system, you can see that we have layers of PMMA and in between layers of our tri-block that self-assemble to create these really nice structures. So we characterize these layers as a function of the extrusion parameters, which I'm not going to detail here, but it allows us to control the size of the layers we make, so from few hundred nanometers to few tens of nanometers. And we can check the structure of our copolymer by, for example, small angle X-ray scattering. And we can see that an hexagonal patterns appear, which says that we have some PMMA cylinders in between a gray polybutyl acrylate region in between the layers of PMMA. And if we now look at the mechanical properties of these multi-layer films and compare them with blends, classical blends, where we just mix the two materials together, and in which we can see this really typical salami nanostructure, we can see that the mechanical properties of both blends and multi-layers are better than virgin PMMA in blue, which means that we have a really large increase in the elongation at break, so the impact properties are enhanced. But what we can see also is that the multi-layer films have better properties in terms of fracture energy than the blends. So by controlling the architecture by creating one more level of architecture, this multi-layer structure, we can reach better properties than blends where we just control the phase separation of the copolymer. So again, this multi-layer system has proved itself. It can make some really interesting materials with properties. I'm not going to mention all of them, but you can find all kinds of papers, mostly for bio groups and also in all groups and some others, about interesting properties for polymer films, dielectric properties, nanofibers, multi-layer foams, gradient layer films, materials that is made of interface, and etc., etc. So now I'm going to switch to the second part of my talk, which is a bit more fundamental, and maybe I'm not going to present everything, but I'm going to say a few words about at least one or two of our more recent work. One interesting application is, I think, is that it makes materials that you have in large amounts. So you have this large amount of films that you can then test with really simple tools such as a rheometer. such as DMTA, such as tensile tests. And because you have this really well-designed structure, you can really get insights on fundamental problems, physical problems about polymer interfaces. So in this study, what we did was made compatibilized films. So it's these compatibilized films I talked about previously. So we made a multi-layer of polyamide 6 and polyethylene. These polymers, they don't like each other at all. So if you just make multi-layer without anything else, you will have really large amount of delamination. So you cannot really achieve this multi-layer structure. So what you have to do is add, again, this compatibilizing agent, which is almost always the same in the industry. In this case, it's polyethylene grafted with maleic anhydride. And this polyethylene will react at the interface with the end groups of polyamide and will form a copolymer, PPA6, that will segregate at the interface. And due to this compatibilizing agent, you will bring some stability to the system, and you can make this really nice multi-layer structure where you control exactly the thickness of each component. And now what we are going to do is do rheological tests of these samples. The thing is, the fusion temperature of these two polymers are really different. So if we fix the temperature well, we can have the polyethylene in the melt state and the PA6 in the solid state. So we are only going to we are only going to see the response, the viscous response of the polyethylene and of this copolymer at the interface. So it's a good tool to study the rheological properties of compatibilizing interfaces, which is, to the best of our knowledge, the first time someone or a group did that. And by tuning the thickness of our layers, we can get access to the rheological properties of the interface. And you can see that when you compare the rheological properties of the interfaces with the rheological properties of the bulk, you have a really large increase of both viscous and loss moduli by 2 to 3, and maybe in some cases 4 orders of magnitude. So you go to really melt material to something that is rubbery. So because this interface is stuck at the interface, despite it's in the melt state, it has a really rubber behavior. And now what we can do with that is we are able to understand the rheological properties of films by only knowing the viscous properties of the interface and of the bulk. And it's kind of mixing rule between the two materials. With only one single parameter, we can fit all the data for all our films really well. And this single parameter is basically the thickness over which the interface and the bulk talk to each other. And what we found is that this thickness is actually quite high. It's on the order of 1 micron. So now we are trying to understand what mechanism can explain this fact that the interface and the bulk see each other over distances that are on the micron scale. And now the last part of my talk is about limitations of the process. So right now I showed nice applications. I also showed that you can raise some fundamental questions with this system. And now I'm going to talk about things that don't work that well. If you remember this plot I presented before, you saw that this is the permeability of the PEO, and it decreases with decreasing thickness. And by looking at the shape, you can say, hey, maybe if I go from 13 nanometers to 10 nanometers in thickness, I can gain 1 more order of magnitude. So let's try that. Of course, Bayer's group, they tried it, but actually the permeability goes up again. And why does it come up again? It's because the layer breaks. So if you look at that under a microscope, you will see things like that. So the layers are broken, and because the layers are broken, the gas can easily find its way through the material, goes from one way to the other, and the permeability goes up. And what we try to understand is, because these instabilities and layer breakups were observed in so many systems, we try to understand the reason why. Is it a physical reason? Is it controlled by the parameter? Can we have some knowledge about that? So what we did is a systematic study of one system. We chose polystyrene and polymethyl methacrylate. Why did we choose this system? It's because it's some kind of a model of immiscible and incompatible blend. This blend has been studied for the last, I don't know, 40 years, and many interfacial parameters have been measured and can be found in the literature. So we studied only this system, but we checked systematically all the processing parameters. So we changed the thickness of the film, the ratio of the two polymers, the number of multiplying elements, and we then characterized the structure of our films. So again, AFM observation in the thickness direction. So what you can see is that for thick layers, you have a continuous system, and you can measure the thickness of each layer. And you can get some statistical information if you measure a number of layers that is large enough. Now, if you try to tune down the thickness, you will start to see some layer breakups, and you can also measure the thickness of the layers that are not broken, and you can measure the number of layers that are broken. And if you try to plot that for every parameter condition, you get some kind of master plot. So here in this master plot, we plot the mean experimental thickness, so the thickness we measure via AFM, as a function of the nominal thickness, which is the thickness we wanted to make that can be, in theory, controlled when you control all the processing parameters. And you can see that you have three regions. One is for films for layers that are above 15 nanometer. And you can see that there is a really good agreement for every experimental condition. So one shape and one color is one experimental condition, which I'm not going to detail. So there is a really good agreement for almost all the conditions we studied for layers above 15 nanometers between what we wanted to make and what we actually made. In the second region, there is some kind of scattering that appears, but some conditions work better than the other. In the third region, which is below 10 or 20 nanometers, you can see that we are always above the nominal thickness, which means that the experimental thickness we measure is always above the thickness we wanted to reach by choosing our processing parameters. This master plot can be linked to another master plot, which is the amount of broken layers in the multi-layer structure as, again, a function of the nominal thickness. And you see that you have these exact three same regions. So above 50 nanometers for almost every processing parameters, no layers are broken. In between 10 and 50 nanometers, well, it depends, but there is a lot of scattering. And below 10 nanometers, almost all the layers are broken, whatever the processing parameters we chose. So what it says, or what it tends to say, is that there is some kind of physical reason that is independent of processing parameters to explain the things that below 10 nanometers, everything is broken. So the first reason you can think of is, okay, it's probably a viscoelastic problem. I talked to you about that before. In coextrusion at the micron scale, viscoelastic problems, they can create some breaking of layers. But we chose to place ourselves in conditions where we have no such differences in viscoelasticities. So we chose conditions where, for two polymers have similar elasticities and viscosities. And the second argument is that we also showed that we are able to reach 50 nanometers continuous layers, whereas when these problems of viscoelasticities occurs, you should see some breaking of the layers at about 1 or 10 microns. So because we have continuous layers well below 10 microns, we think that this is not the nature. So I'm just going to conclude with what we think it is. So to explain this critical thickness hypothesis, what we think is that what we have is similar to the problem of the dewetting of thin polymer films. So here I'm looking at polymer thin film, so 15 nanometers or so polymer on top of a substrate from the top. So it's only one layer, it's not a multi-layer system. But if you put this 50 nanometer layer on top of a substrate with which it has no affinity, and you heat that above the TG of the glassy polymer, it will spontaneously create some holes, and these holes will grow, and the material that was in the film will segregate in the rim around the hole, and it will form, at the end, it will coalesce and form this kind of droplets. So the mechanism basically is that you have some thermal waves at the interface due to thermal energy, for example. And when the layers are thin enough, due to van der Waals interactions, the initial instability will be amplified by the van der Waals interaction, say, of the PMMA layers that will see each other in between the PS layer. If you put some numbers in that, the critical thickness at which the van der Waals interaction becomes dominant over Laplace pressure will give you typical numbers on the order of 10 nanometers. So it's really similar to what we saw in our multi-layer system. And also the time at which it breaks, the equation is written here, and I will not detail it, but if you put some numbers in there, you can see that the typical time is about 1 second. And it's really short because the extrusion process lasts 1 minute. So if everything breaks in 1 second, then at the end of your extrusion process, everything is broken. So I'm not going, because it's already 45 minutes, I'm not going to present that. So I'm going to skip that part, but you can check that later on. But what we did was trying to build model experiments to confirm this hypothesis, because at this stage it's only hypothesis. So we designed dewetting experiments to try to confirm what happened in the polymer co-extrusion process. So we design an experiment where you can check the dewetting, and then we design a simple model that I'm not going to talk about now, but that allows us to model the dewetting of our thin films. And with that, I'm going to conclude by saying that I hope I showed multi-layer co-extrusion is an interesting processing tool, because processing is usually, people think it's not that interesting, but I hope I showed that you can do some interesting stuff with nice processing tools, both for applications, materials with improved properties, but also for fundamental studies. And with that, I want to thank all the colleagues, and all the fundings agencies for this work, all this work. So it's a mixture of many small projects that I try to bring together. So that's why there are many people. And I hope you enjoyed it. And I'm happy to take questions if you have them. Thanks for your attention.
Thank you, Guillaume. It was a brilliant talk, and there are already questions which have been asked. So, okay, as chair, I will read the questions. from the audience. So the first one is which type of interaction governs the, I don't know, intercalation or interaction between layer by layer materials. So I don't know if I just read the question, but I think the idea is what are the possible interaction between the two polymer layers in the multilamellar films?
Yeah, so I think mostly it's van der Waals interactions. It can be also hydrogen bonds in sometimes. And in the case of if you add a copolymer, yeah, the copolymer will segregate at the interface. And because each part of the copolymer is going in the phase it likes, you can create some entanglements. So I don't know if entanglements can be considered as interaction, but that's what will tie the layers together.
Okay, so it's more physical type interaction. But the second question is a bit related. So in which case the blend of the two polymers could be considered as copolymer? I think it was the case of polyamide and polyethylene when there was this maleic anhydride reaction. So is it only when there is a reaction in the extruder that you can speak of copolymer in that case?
Yeah, I think so. So there are different strategies to. So in some cases, polymers are compatible enough by themselves that you don't have to add a copolymer or a compatibilizer. But in many cases, you have to do that. And there are different strategies to do that. So in this case, it's kind of, in the case I presented, it's kind of reactive extrusion because there will be a chemical reaction in the extruder during the extrusion. So polyethylene with the grafted maleic anhydride will react with the polyamide because the end chain of the polyamide is an amine, and it reacts really quickly with the maleic anhydride. So in that case, the copolymer is made in situ. In some other case, you can add a third extruder and you add the copolymer directly in the middle, in between the two layers. So you don't need a chemical reaction. You just need to add one more extruder. And in some cases, I guess the compatibilizing agent does not have to be a copolymer. It can be some kind of molecule that will like the two polymers, but in most cases, it's copolymer. I don't know if I answered the question.
Maybe I add one. There was another case. It was with the triblock, this MAM, PMMA, polybutylacrylate, PMMA. So it is a triblock. So I guess you need a certain quantity because you need to fill the extruder with this triblock. So yeah. Do you have, and we know that block copolymers are somehow more expensive or more difficult to synthesize than homopolymers. So what is the minimum amount of copolymer you need to use it, not as a compatibilizer, but as a single layer?
As a component, yeah. Yeah,
so component, yes.
It's a really good question. So yeah, I have to first say again that usually polymer we use that in the extrusion are on the order of a few kilograms, maybe sometimes few tens of kilograms. So usually it's polymers with a large dispersity index with many additives. And because our in the lab or process use screws with relatively small diameters, we can go a bit below that. We are limited by the ratio of the two polymers. If you want to do coextrusion, you cannot do less than 10%, say, of one polymer with respect to the other. So we can go as low as 500 grams, something like that. But still, it's a good question. Not many copolymers can be found by the kilo. And so these copolymers were provided to us by Arkema. And these kind of polymers, because they are added as additives and maybe at relatively large quantities as impact additives, they made some kilograms. So it's not as well defined as copolymer made in the lab. And I think 1/3 of it is actually homopolymer because some part is unreacted and they don't wash that really well. But Arkema give it to us, and I think when you buy it, it's quite expensive.
So you can cope with some polydispersity in some case.
Yeah, and I think so. It's a tricky question that we had and we wanted to tackle, but we had never really found the way to do that properly. We actually think that in our case, polydispersity helps us rather than does not help us. But it's only a hunch. We don't have proof of that, and to prove that, we would have to be able to find 10 kilograms of one really monodispersed polymer to try to compare. But I think polydispersity helps us rather than not.
Okay, so now we take a question from YouTube by Lenny Van Dale. The question is, okay, as you said, for co-extrusion, similar properties are required, at least rheological properties.
Yeah.
So the question is, what are the typical shear rates obtained during the co-extrusion, and can you? So what is the range?
It depends on where you are in the co-extruder, because when you are in the die or when you are in the channel, but usually it's in between 1 to 10
inverse second, or
yeah, inverse second.
Okay.
Usually look at what happens around 10, and we go a bit below and a bit above. And it cannot be an exact match in all the range, but it has to be, say, less than a factor of 2 or 3 different in the whole range for it to work.
And the two polymers, when they are different, like the polyamide or polyethylene, how do you match the melting temperature if they are too different? Can you use a single temperature for the two polymers?
Yeah, we have to for the co-extrusion, it has to be all in the melt. So we have to find the correct temperature for polyamide and polyethylene to work together. So it's not that easy. The thing is, polyethylene melts at a much lower temperature, but the chances it's quite stable with temperature. So you can increase the temperature and it won't degrade that much during the extrusion time. But for polyamide and other polymers, it can be really complicated because the window, the process window for polyamide is really small because it will degrade really fast. So yeah, we have to find a compromise for the two polymers at some point when in the co-extrusion setup where the two flows are working together and separate themselves and recombine, there is only one temperature.
Okay. We have several questions by Etienne Gros. So I read the first one. Can we obtain other microstructure than lamella, for example, cylinder?
For the copolymers?
I guess for the semi-crystalline polymers.
For the semi-crystalline, yeah. So
maybe with copolymers.
I cheated a bit by showing only polymers that work. So that they work because they make lamellas, but I don't have an example in mind of one polymer, but I know that some of them, for example, when you confine them, some semi-crystalline polymer, they just don't crystallize anymore. So, and some of them also, or instead of doing lamellas that are oriented in the right direction, so the extrusion direction, they make perpendicular lamellas. And this one is totally not barrier because in between two lamellas, the gas will go through. So you really have to check between in plane and out of plane lamellas and maybe no lamellas. But yes, you can have different structure. And I guess yes.
I have a somehow related question. It was on slide number 30, if you can show. There was a beautiful IFM image. So you said it is a phase IFM. So the color is false color that give you the toughness of the polymer. So I guess the dark one is the glassy one, and
so they are both glassy in that case.
Okay.
PS and PMMA, and actually I don't. You didn't really ask your question, but I think I get.
No, the question is why do we see ripples which are perpendicular? Is there some? We see the yes.
I think it is the cutting that is not perfect, and so you see some.
So you don't have a perpendicular instability in some case, or?
No, I think no. I think because we are really in the glassy state, so and well below TG because it's PS and PMMA. So I think it's just it shows the cutting.
Okay.
So so I don't really understand, or I can't really explain, because PS and PMMA, they have really similar properties, rheological and mechanical, both glassy, same TG, but you really see them really well in AFM. The thing is, depending on the sample, this is not always the same color that shows. So sometimes PMMA is brown and sometimes it's yellow. And we don't really have all the explanations, but we just see that we see them really well.
Okay. Yeah, the image are both beautiful. Congratulations.
So I'm not doing them, but the students are really.
Yes. we know that the students are doing the experiment. We have another question. That one more by Etienne. Is it? I mean, the first one he asked: is it industrially? Can you make it commercial, or is it doing in industry? And can you do it with bio-based polymers such as PLA, PHA?
Yeah. So yes, for both questions. So the first one with some, I mean, you have to be a bit careful, but as I said, it came from the industry. So I think some applications are commercial, but it's really small.
But the nano one, the one with the nano layers like you did.
Yeah, I think the iridescent films are nano layers. I'm not sure, but I think. And Eric Baer, so Professor Baer, developed a startup company to try to commercialize some of these films with dielectric properties. I think he worked. And so I don't know if it's a success or not, but the company exists. So it's ongoing business for the last 5 years. And for the second question, I didn't present it, but because it's mostly work by Cyril, Alain, and Mathieu, who is not there. But yes, they work quite a lot with PLA, and they look at the crystallization of PLA when it's confined in nanolayers for barrier applications. And we also did some work with PHB, another bio-based polymer, which is a bit more difficult to work with because it's a bit less stable, and depending on when you buy it, it can be quite different from one batch to the other.
I think we can take questions from the audience on Zoom. If anyone has a question, please open your mic, and even your camera if you want. If you prefer, type the message. Maybe I can.
Hello.
I can. Yes, there is one.
Yeah. Hi. Thanks for your nice presentation. And yes, you answered correctly my first two questions. So from that, can we say that only chemical reactions between two polymers will generate a copolymer? Otherwise, will be a blend.
If you have an interface reaction, it will still be a blend, but the copolymer at the interface will help to have for the blend to have. So, and without chemical reaction, it also will be a blend, but in many cases, the blend won't have good properties. So, for example, the HIPS, high impact polystyrene, it's a rubber in polystyrene. It's some rubber in polystyrene, but there is also a chemical reaction at the interface between the rubber phase and the polystyrene phase to have the blend more stable and with better properties. So you don't always have to have a chemical reaction at the interface, but most polymers are incompatible and immiscible. It's usually required for industrial applications. Otherwise, the blend won't be good enough to meet the industrial requirements in terms of properties. Is it clear or?
Yes, thank you very much for your explanation.
Thank you.
Okay, maybe I have other ones. Yes, also the end where you speak about the instability, the dewetting, that was very interesting.
Sorry, I have to skip that part a bit, but maybe some other time.
Yeah, this intercalated dewetting is especially with the case where you have solid layers and fluid layers between them, and you do the rheology. So I think you still have a lot of experiments to perform and study this very interesting system.
Yeah.
And
yeah, we are looking for a PhD student for this experiment.
Okay, so it's a good time to advertise for if you have a PhD grant. And I was curious because you cite this paper by Carrie Dalnoky-Verres from Canada, the one where, like a 20 years old paper, where it was the beginning of this story of effect of the thickness on the TG value. So in your case, because you can make very thin layers, did you see effect of the layer thickness on the TG value of the polymer?
That's a really good question.